Hello everyone, my name is ATANASOVA and today I will be presenting computer-based optimization of algorithms for the experimental analysis of wind turbines in energy generation. So to start first, we will be saying some research objectives, methodology and the impact and the contribution that we want to achieve with our presentation. So our research objective is to develop a optimization framework. We use here Python to enhance algorithms used in the experimental analysis of wind turbines. The methodology that we are using is integration of empirical, analytical, and machine learning approaches to validate and do evaluation of the model performance under diverse European climates, meaning we are mostly using countries from Central and from Western Europe, and we are comparing them and seeing how the wind production is in all those regions. And the impact and the contribution is to reduce the computational processing time, improve the turbine placement decisions, and advanced modern sustainable energy technologies. So first, we will be saying that in more detail what is our research and what are in more detail our objectives. So the key parameters that we are analyzing are the environmental, mechanical, and the regional scope. So from the environmental, we are analyzing the wind speed, the humidity, and the stochastic regional climates. From the mechanical, we are analyzing the turbine design, mechanical components of the turbines, and the structural dynamics. So from the regional scope, we are doing, as I already said, a comparison between the Western and the Central European countries. So the core research objectives and what we want to deliver are to first identify the models, make a comparison between the performance of all those models, and what are the factors that influence in making those models being bad or being good, let's say. So for identification of the models, we systematically do it, and we analyze the mostly common used algorithms and mathematical models for forecasting and analyzing the wind turbines. So for the performance comparison, we are comparing real data, meaning real energy production data across multiple European countries to highlight the strengths and the operational limits, and the influencing factors are to investigate specific environmental and mechanical variables. So the goal of all this project is to propose the optimal model that's combination of multiple models and will result with production optimization. So here we are starting with the results and our discussion for the models regarding their performance and their structural dynamics. We did separation in three main fields. That's the energy production, the resonance and the vibration, and the comparison between multiple models. As we already know, the wind forces usually move non-linearly, which directly influence the system velocities, the displacement, and the multi-year energy outputs. So regarding the multi-year energy spikes, usually, what our results are showing is that the years 2019 and 2023 showed higher energy production that confirmed that the critical importance of multi-year analysis for effective planning wind turbines. Where is this coming from is that if we are following only, let's say, 2 to 3 years, how the wind moves, then we build some turbines in some certain location, we might still face some difficulties where the wind in the next few years might be slower, and then the production will be slower. So that's why it's always better to have bigger range of analyzing. The rotor size balance is also very important, and our research shows that smaller rotor areas are better than the larger one, because when you have a larger rotor area, that means that we need stronger wind in order to move the turbines, and the production might result with smaller production. So we need to be very careful which sizes of turbines in what location we are putting based on the winds. So the frequency shifts, dominant frequency varies yearly, which present reasoning risks in the turbine's natural frequency to match the wind's expected frequencies. Here we also did some fast Fourier transformation analysis, which identified that the yearly dominant vibration of frequencies in order to prevent the matches that is crucial to safeguard structural stability and to prevent long-term damages. Regarding the model comparison, there are two models for comparing, and that's the single degree of freedom model, which provides a simple, effective, and rapid representation of turbine dynamics over multiple years, and the advanced FEM simulations, meaning finite element methods that are detailed for stress and deformation distribution under the more complex loading of the turbines. On this slide, we have a correlation heat map, which is measured on 12 European countries and reveals the wind speed as the dominant positive driver, while the temperature and the prescription displays are weaker, nonlinear negative constraints on multi-year wind energy productions. So the chart uses a scale where the values that are closer to 1 are usually darker and indicate a stronger positive correlation, while the values that are near 0 are the lighter gray, which indicates no correlation, or negative values that indicate an inverse relationship. So first we have measured the wind speed here in the column, and this shows a strong positive correlation, which is likely the strongest correlation with the wind energy across a single country. The consistency of the correlations, the values are exceptionally high, especially in Slovenia, where it's 0.75, and then in Germany, where it's 0.88, Poland, Slovakia, which makes very logical sense, because as the wind speed is the fundamental variable for generating wind power. So the other values that we have are the weak negative drivers, which is the temperature variables. These have usually, we are talking about these three, have inverse relationship, which means that the average temperature at 2 meters, the maximum temperature, and the minimum temperature, they all show a negative correlation across the board. The values vary between 0.10, minus 0.10, and minus 0.33. What are these results actually saying is that the wind energy generation tends to be higher if the temperatures are lower. So this is common pattern in Europe, where winter months typically experience a stronger and more consistent, let's say, wind pattern compared to the calmer, warmer summer months, and in the regions that are more central than the regions that are more south or more east. Then we have the solar and the sky parameters. Here we have no correlation. I mean, the parameters shows particularly zero correlation. values across all the countries are between minus 0.03 and 0. So this means that sunny or cloudy days have no direct mathematical relationship with how much wind energy is produced in the dataset. We have also minor secondary factors. These also show weak correlations, meaning that they are poor independent predictors of the wind energy, though they still show some varying trends, except in a few countries. For example, the relative humidity shows weak positive correlation, mostly between 0.11 and 0.20 and 0.22, except in Slovenia. So as the summary from the heat map, we can say that we have reliable, highly correlated parameters for the wind energy generation with the wind speed dominance, and the other variables mostly reflect to secondary seasonal winter patterns that are in fact colder, stormier weather. Here we have correlation of meteorological parameters with wind energy production over all the 12 countries in the 10 years period, while we are highlighting as industrial and geographical divide between Central Europe leaders and developed Balkan markets. So the top producers of energy are, of course, the more central, highly developed countries like Germany, which is the leader here, with Poland following Germany with roughly 950 per production. So in the middle we have Slovenia, Czechia, and in the upper middle we have Slovenia and Czechia. With the lower middle we have Serbia and Austria, and then we have following the Balkan countries with topping Montenegro, Croatia, Albania, Kosovo, Bosnia, and Slovenia. In Slovenia we have almost no registered visible production, and the trend here illustrates that the contrast in the wind energy generation among these specific nations heavily dominate also on the region output, accounting for the majority of total production shown. Meanwhile, the Balkan countries compared to the central countries are way behind. Here we have comparison of average wind energy production per region, meaning in Central Europe we have 670, while in the Western Balkans we have 270. So these inequality drivers are based on infrastructural divide, natural and topographical advantages, and the policy and efficiency advancements. So the infrastructural divide is developed wind infrastructure is heavier in the Central Europe than in the Western Balkans. The Central Europe also benefits from more favorable topographical and meteorological conditions, and the regional policies and enhancements are supporting more in Central Europe compared to the Western Balkans developing strategies. Here we have the average correlation of meteorological parameters with wind energy production, and we can see that the wind speed is the most common one, and then it's followed by the humidity and the prescription, while the temperature and solar radiation and all other meteorological parameters are not that important for putting into consideration, as it's the wind, the humidity, and the prescription. We can see that all temperature parameters show negative correlations, indicating that the higher ambient temperature restricts air density and reduces the turbine performance, with a more produced effect in the Central Europe than in the Western Balkans. And the humidity and the corrected prescription displays moderate positive correlation, which is which surface pressure negatively correlates with production due to its inverse relation with the regional atmospheric wind activity. Here we have the average correlation of parameters with wind energy by region, and this charts on this chart, the values that are closer to 1 indicate a stronger positive relationship, and the values that are near 0 indicates no relationship, and a negative value meaning inverse relationship. So the dominant, as we already said, is the wind, and here the values in both regions show extremely high positive correlation of approximately 0.85. The Central Europe has higher correlation than in the Western Balkans, but the difference is still not that big. Meaning that the negative predictors, the temperatures are let's say negative. We have negative correlation roughly with 0.15 to 0.20, with Western Balkans again showing slightly stronger negative correlation than in Central Europe. Then we have the humidity, which have a weak positive correlation, roughly 0.10 to 0.18, which here we have more humidity in the Western Balkans than in the Central Europe. No correlation we have in the solar radiation, and as a summary we can say that So here we will be talking about dynamic model analysis and characteristic behavior. We are doing systematic comparison of characteristics between the three countries, Albania, Austria, and Bosnia and Herzegovina, and the characteristics that we are analyzing are the time behavior, characteristical amplitude, relation to the model mode, and damping and duration. Regarding the characteristic amplitude, we can see that Austria is the leading country, followed by Albania and Bosnia. Regarding the time behavior, we have different behaviors in all three countries. In Albania, we have drift and slow variation. In Austria, a significant resonant increase. And in Bosnia, we have high model bursts. Relation to the model mode, in Austria, we have Austria aligns closely, let's say, with the first and the second frequencies, which contributes to its strong resonance. Bosnia tends to activate higher modes, while in Albania we don't have any specific identifiable mode according to the data that we have collected. The damping refers and the duration in Bosnia has the most pronounced damping, described as more damped and smaller, meaning its energy dissipates quickly. Albania exhibits a damping that becomes noticeable over the time, and in Austria we have drift weeks and some weeks that are richer with energy. As in the previous slide, here we have different countries. So in the table 3 presents the characteristics of amplitude similar to those that we already observed in Albania, Austria, and Bosnia, with Germany showing the smallest values. Croatia displays a slow drift over time, while Czech Republic experienced significant resonant increases, and Germany experienced frequent high model bursts. Model relations follow the same trend, with resonance in the Czech Republic and higher mode activation in Germany, and the damping is most evident in Germany and the least evident in the Czech Republic. In the table 4, we are presenting the data where Kosovo amplitude ranges in moderate, while Slovenia and Slovakia have wider ranges. The time behavior shifts from slow drifts in Kosovo to rare but high oscillation in Slovenia, and to high model burst in Slovakia. The relation to the model for Kosovo, we don't have data. For Slovenia, it matches closely to the resonance, and in Slovakia, it activates higher models, and the damping and the duration is noticeable over time in Kosovo, more damped and smaller in Slovakia, and it drifts the energy in Slovenia. So here at the end we have some conclusion and recommendations. So this study validates the significant impact of real meteorological data on dynamic wind turbine performances, verifying the predictive accuracy of applied mathematics and the models. So the key experimental findings are the model accuracy, dynamic insights, peak generations, and neural network discovery. And as recommendation is to integrate some modeling frameworks to make more adaptive optimization, meaning to adapt the turbine growth or dimension dynamically to match a specific local and meteorological locations, and to have risk mitigation and safety, meaning to perform more analysis before deciding what place to put the turbines on. So that is all for this presentation, and thank you so much for your attention.